Good day, everybody, and welcome to our presentation on fiber loop mirror sensor design. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be assisting your host, Ahmed Attia, with any questions you may have. At the end of the presentation, we will hold a short question and answer period in which we'll take questions via the questions section only. So please do not use the raised hand option. Now, if you look over on the GoToWebinar control panel, you'll find a PowerPoint presentation, or actually a PDF of this presentation in the handouts section. Feel free to download that at any time. And lastly, we'll be recording this webinar and emailing the link to everybody 1 hour after it concludes. And with all our webinars that we host, we actually have a page on the website which lists all the webinars there, and you can watch the recorded videos at any time that you choose. With that said, let's get the webinar underway. I'd like to introduce your host, Director of Optical Systems, Ahmed Attia.
Yes, good morning, everyone. Thanks for attending today's webinar, which would be on sensors in general, and specifically on using fiber brick gratings in a loop mirror configuration to provide accessibility enhancement of the sensor. The presentation would include the following topics. I'm going to talk about the FBG component in OptiSystem and the different applications of it. Then I'm going to describe the optical loop mirror, which is known as Zagnag interferometer. And then I'm going to talk about the sensing capabilities of OptiSystem. Then I'm going to describe the component used usually to build a project for OptiSystem for sensors. And then I'm going to mention some information about Phi OTDR for vibration sensing. And then I'm going to show you some examples and then end the presentation with questions and answers. So for the fiber brick grating in OptiSystem, you may find this component in different locations. You might find it as part of the software enhancement of OptiSystem, where Optic grating software component is added there. And you might find it under default OptiWave software tools, Optic grating. And as you see it here, basically in this location, this is the component, and then in the component here, you can set up the center wavelength, or you can load your own spectral characteristics of a grating if you design it in Optic grating. Then you might find fiber brick grating in the filter library under Optical and FBG, where you have 4 components there. This component can be used for dispersion compensation or for filter characteristics or reflection characteristics. Also, you may find the fiber brick grating component under sensor library in the default. And this component, basically, the main component we're going to use in today's webinar for sensing applications. And the component basically have a feature in it, one of the tabs, where you may control the temperature or stress or strain. I'm going to show these features later on in a live example. And now in the near future, in OptiSystem 16, we're going to introduce a new component, which is, it will be a fiber brick grating component where you design your own grating and use that grating for sensing application. Okay. Now, this component at this moment is designed using a C++ component in OptiSystem, as you see it here. And this component basically has the sensing feature and also has the capability to design all the parameters of a fiber brick grating, as you see in this kind of windows. Okay. Now, the second part of the components, major components we use here is the loop mirror, fiber loop mirror, which is called Zagnag interferometer. And the Zagnag interferometer, basically, it's a very simple component made up of a fiber coupler and with terminals connected to each other. Now, different configurations could be available by adding up more components inside the loop here. We call it the loop, and this could be polarization controller, could be amplifier, could be fiber, could be phase shifter, and in our application today, we're going to add up a grating inside the loop and then look at the performance of this this loop. Now the loop, how it works, basically, you launch your input signal here on this path, which is in the black arrow, and it goes into terminal 1 of the fiber coupler. Now the fiber coupler splits the signal, depends on the coupling ratio of it, into a clockwise direction and the counterclockwise direction, as you see here. Now inside the loop, if the phase of the electric field in the clockwise direction and the counterclockwise direction encounter no phase change, then when they propagate all the way back to the point here at 4 and back to the point 3, they will interfere either constructively or destructively based on the phase difference. So if the phase difference between the electric field in the clockwise direction and the counterclockwise direction equal to 0, then the signal would be basically reflected back and no signal would be transmitted into this path here, in this path at terminal 2. If the phase difference between the clockwise direction and counterclockwise direction is 180 degrees, then the signal, suppose when they interfere here, it interfere destructively on this path and constructively on this path, and the signal you're going to be see it as transmitted signal. So the idea here is what you can do, you can control the phase difference between the two the fields in the both directions, either again using polarization controller, phase shifter, or exploit the nonlinear effect in the optical fiber, for example, and create a phase for this electric field difference between the clockwise and counterclockwise. Now the switching capabilities, if you set up the coupling ratio here doesn't equal to 0.5, it means the electric field in both directions are not equal, and then when encounter, let's for example nonlinear effect inside the loop, then the phase shift for the clockwise and counterclockwise would be different, and that's why we need to be not equal to 0.5. However, if you make the coupling ratio here equals to 0.5, then you need to add up some other components to make a difference in the signal, the field level, and that could be achieved using optical amplifier, for example, placed on one end of the loop, where the signal will be amplified in one direction and getting a nonlinear phase shift different than the other component where it doesn't amplify in the fiber. Let's say, for example, if you place a fiber in this loop. The other way is to place a phase shifter like a polarization controller or any other phase shifting mechanism like liquid crystals or a Mach-Zehnder modulator, whatever you can have as a phase shifting mechanism in here, so you make a difference between the clockwise and counterclockwise electric field propagated in the loop. With these kind of mechanisms, you should be able to control the switching of the signal, incoming signal, into either going back again, reflected back into terminal 1 or transmitted to terminal 2. This diagram here shows you, for example, a switching feature of the loop mirror, very simple loop mirror. It's just only connecting the two arms of the loop with a phase shifter in place. And if you look here at, for example, when the phase shifter is equal to 0, arm 2, which is the transmitted path, has 0 power, so all the signal is going through the reflected path. Now if you put 180 degrees here, then the signal goes all of it is through the transmitted path, which is arm 2, and 0 almost to going through the reflected path. You have to, if you go back again here, if the phase shift between the counterclockwise and the clockwise direction of field directions is not 0 or not 180 degrees, then you're gonna see the signal at both terminals here, reflected and transmitted path. So sometimes for some applications it's good to see it on both arms. Some applications you don't need to see it on both arms. We need to see it on single arm, and that's why you need some kind of control of the phase inside the loop. Okay. Now in OptiSystem here we have an example which is basically I'm going to run it later on in the webinar and show you how the loop mirror switch is designed. As you see, you have a laser source, for example, passes through an isolator and through a directional coupler here, where the coupling ratio is set like at 55%. So it means 55% is going to go through this terminal, and 45% of the electric field or the power is going to go through this direction. And then the clockwise direction is going to go through a nonlinear fiber. This is very highly nonlinear fiber of about 10 kilometer length and certain nonlinear parameters, as you see here. And then it goes through, coming back again to this direction. The counterclockwise goes that direction, which is less, so it encounter less phase. And then eventually you're gonna see either the signal on this path and that path. Again, the main component in this this diagram, as you see, is the laser diode, the fiber coupler. One important in this kind of components where you have bidirectional components, you need to make sure that you insert a delay elements here to allow the propagation in the backward direction to be calculated. And also you have to make sure that if you don't have any terminal connected to an input port of the direction coupler, you have to put an optical null to allow this component to be calculated in OptiSystem. So this is very important things which is has to be taken into account while you do your simulations. Now, here I'm going to describe some of the applications which is you may find in the literature for fiber loop mirrors. And as I showed you earlier, switching is one of the major applications. Then you can use it for gyroscopes to measure phase, and then you might use it for signal demultiplexing. You might use it for optical signal amplification, for fiber lasers. You may use it in sensors, as we're gonna do later on in this webinar. You might use it for protection switching, for clock recovery, for signal regeneration, and so on. Okay, so OptiSystem sensing capabilities at this moment, we offer a wide variety of sensing, which basically based on FBG applications. But this is the major sensing feature in OptiSystem, where we can sense the temperature, stress or strain at different locations in the fiber. And also we can, if with the design which is coming up very soon, we can model the water salinity measurements of using the fiber brag grating. Another this is like this this application is developed based on this paper, which is published in 2002. Also, we have an OptiSystem is coming up in version 16, a Phi OTDR, which is based on relay backscattering to measure vibration in optical fibers. I'm going to talk briefly about the Phi OTDR and about the water salinity, where we have two separate webinars. It's going to be given for these two components. Okay, so for fiber brag grating sensing applications for temperature, stress, and strain, basically the models which we have today can be applied to do like sensing modeling. So, for example, you place a grating somewhere in location in the fiber link, and then you measure temperature or stress or strain at that location. You can see, for example, the quality of the signal, the maximum distance, the power levels. So you can do lots of modeling for sensing using fiber brag grating. This is one application you can use using OptiSystem. The other application, which is used for synthesis of the FBG. So, for example, you can have measured data, and then what you do is you would use the measured data to design or to find the parameters of the fiber brag grating, if you like, which is used basically to characterize or to get the measurements. So this is the synthesis feature of the FBG, and that's where the salinity sensing application was done. So using the synthesis application, so we have measured data, and then we created the grating, which has that feature to measure. And then eventually, once you create the grating, you can use it for later measurements and modeling. The other thing is when you have multiple environmental conditions, for example, stress, strain, and temperature variation at a certain location, it's very difficult to distinguish between these conditions. So what you do, basically, you can use the modeling using OptiSystem to kind of isolate using the synthesis application feature of the OptiSystem, where you can find exactly what is the effect at the certain location, which causes the variation basically of the fiber bright grating center wavelength, as we're going to show you later on. Okay, so the models which is used in the sensing feature of FBG in OptiSystem is based on deviation of the center wavelength of the grating, which is the bright grating, and this is given based on the variation of the photoelastic coefficient, which is PI. Now, we need to note some people have a measurement or values for the photoelastic coefficient. Some people, they do have another parameters called gauge factor. So the gauge factor is related to the photoelastic coefficient through this relationship. And then in this equation here, basically the alpha is the grating thermal expansion coefficient, which is given usually for the grating, thermo-optic coefficient, which is alpha TO, and delta T is the change in temperature. With that and the epsilon, which is the longitudinal strain parameter, all these parameters, which is stress, strain, temperature variation, can cause a shift in the grating center wavelength, which will be calculated basically and given for certain conditions. Now, the strain parameter, the longitudinal strain parameter, epsilon is given as function of the longitudinal, which is the sigma ZZ, and the transverse component, which is the sigma XX and sigma YY components. The E here is the Young's modulus, and the nu is the Poisson ratio. These models, it can be found in this reference here. Okay, now the implementation in OptiSystem for the FBG to be used as a sensor, you might have it as a standard implementation where you have the grating basically placed somewhere along the length of the fiber link, or you might have it using this loop mirror implementation, which its main topic in this webinar. Now, there is a difference, advantages and disadvantages of the standard form. One of it is you can have only single axis capability. I'm going to show it to you later on. However, the loop mirror implementation, you may have access from both directions. So, for example, you can monitor from west side or east side of the link which you have placed these sensors on it. Then also you can have controllability of the access point. So if you wanted, you just give access only to the west side, or you can give access to the east side, or you can give access to both sides if you like. Now, another advantage of the loop mirror is because of the nature of the loop mirror based on the interference between the clockwise and counterclockwise fields, and mostly sensing application uses ASE sources or using light emitting diodes where the light is not coherent, and which means that when the light is interfering at the coupler when it goes through the loop, half of the noise is going to go to one terminal and the other half of the noise is going to go. So the noise would be lower by 3 dB basically in every time you have output on either arm. And just is improving basically the signal to noise ratio of your system. Okay. In this part here, basically the FBG is implemented in the standard form. Again, it's you have, for example, a source where your location, let's say this station here is your station where you monitor and you transmit your signal. Signal again could be broadband source, let's say, for example, ASE source or LAD. Transmitted through a circulator. Circulator direct the light from terminal 1 to 2 and go through the fiber. So the grating can be placed at different locations along the link of the optical fiber, and the grating center wavelength can be chosen at different wavelengths. And the advantage of doing that, this center wavelength can be used for basically this center wavelength can be used to detect the location. So for example, at this location, which is for example 10 kilometer of fiber, I have the grating lambda 1. After another 10 kilometer, I have lambda 2. Another 10 kilometer, I have lambda 3. So I know if I measure lambda 3, it means after 30 kilometers, or lambda 1, it's after 10 kilometers, and so on. Now, based on the reflection characteristics and the transmission characteristic of the grating, the light is going to come back again to this terminal 2 and then directed to terminal 3, where you're detecting that using either power meter, or you're using a spectrum analyzer or something like that, depends on your setup. Now, the center wavelength, as we showed earlier, the Bragg wavelength is affected by the environmental condition at the location where it's placed. So if temperature changes, or stress or strain changes, then this center wavelength is going to drift and causing sensing capabilities, or provide sensing capabilities for the grating. Here's an example in OptiSystem, which I'm going to run it later on. Shows the grating, which is placed at different locations. On, for example, you can imagine it as on a bridge, and this grating broadband source here is used to transmit the signal through this grating. These gratings are set at different wavelengths, and the conditions, let's say some places have only temperature, some places have only strain. So you can do different kind of modelings again, and use the capabilities of the grating to do the synthesis if you like to do that. In this example here, show you the issue of accessibility of this standard representation. For example, these gratings, one of them is located at the source, another one is after 10 kilometers, another one after another 10 kilometers is 20 kilometers from this location, and the third one is at the same location here. This one is measuring stress and temperature variation. These three measuring only temperature variation. I'm going to show you this example later on. As you see in the reflection path, which if you measure using this component, which is called interrogator, you're going to see these wavelengths basically generated because of the bandwidth of the grating, and each one is at different wavelengths, which tell us the location where it is. And the other thing is, if you look at the transmitted path here, you're going to see these depths here, where is the grating filtering happening. Now, if the detection scheme here is sophisticated, let's say you have spectrum analyzer and you can detect the peak, then you can detect it. But most of the simplified system, you use power meters, so sometimes with filters, sometimes it's difficult to measure their transmitted signal. So this example which I showed you, it's run at the temperature for the first grating running from 19 degrees to 58 degrees, and you can see the center wavelength drifts over this range. Second wavelength also after 10 kilometer and at temperature range from 19 to 58. The third wavelength is at 20 kilometers, so you can see the power level how it goes down because of the length of the fiber. So this is something which is advantageous in OptiSystem, where you might add up, for example, in your modeling, optical amplifiers to amplify the signal to do, for example, power budgeting, make sure that the signal is received at the destination properly. And this here, in this last grating, which is located at 20 kilometer, again, we have two effects, which is temperature and strain effects. And these two components I'm going to show you later on, they have certain profile where you can enter your own profile for strain or temperature and do the modeling over it. And you can see that because we have two effects here, the strain and temperature, the variation of the center wavelength is wider, and that's the advantage of OptiSystem. Again, it can give you a mechanism to isolate these effects. Okay, now we're going to move into the main topic of this presentation, which is the fiber loops sensor using FBG. So the design is as shown here. You have the fiber coupler, which is, in this case, we use 3 dB coupler, which is 50%, which means 50% of the light going here, 50% goes of the light here. And then we place a phase shifter in it. So in this path, we're gonna add up the phase or subtract the phase, depends on the setting. And then this is a fiber Bragg grating, which is exactly the same grating used in the standard form. So the signal going to be reflected back here, part of it, and transmitted the other part. And the counterclockwise signal comes here. It's going to reflect it, and part of it's going to go here, and then go through the phase shifter, and then it's going to be interfering at these two arms. Now, if the phase shifter, I'm going to show you, it's set to 0, the signal is going to be basically reflected back. If the phase shifter is set into 180 degrees, the signal would be transmitted through the path. So this path would be the transmitted path, which, for example, you can locate it at east side, for example, of the link, and the this path, which is the reflected path, can be set at the west end. So you can, by adjusting the phase of the phase shifter inside the loop here, where you place the grating, you can control where the signal to be. Now, this is, we have a publication here, as you see, which is done, which was presented in at the conference of sensing applications, defense and sensing applications in 2018 in April. Okay, so this is just a quick list of the light emitting diodes which you can use, for example, commercially. You can buy them from Thorlab or Q Photonics or Shimadzu Scientific Instruments and Hamamatsu. And every one of these LEDs has certain width and certain center frequencies. And then you can use these commercial values, commercial specifications in the simulation. This is the setup of the loop mirror. As you can see, this is the LED biased with the DC bias going through the circulator into the fiber coupler, into the phase shifter here, and then into the grating, and then back to the directional coupler. And you can measure the reflected signal here, or sorry, the transmitted signal here. And this is the signal can go directly into the circulator and pass into this is actually, this is supposed to be reflected, and this is supposed to be transmitted. This is a sample of the signal we're gonna see in the simulation once we run it. Okay. Now, the parameters used in the simulation, this is basically, you can set up the laser LED bandwidth, center frequency, the grating parameters, for example, the effective index, modulation, and then you can control the temperature. For example, you can change it from certain range. You have to set up the other parameters of the grating to, if you wanted, for example, to include stress or strain or whatever parameters, you can set it up in the grating, as we're going to show you later on. Okay, so in the light emitting diode, as if I measure it between the 1540 nanometer, 1560 nanometer at this moment, because the grating is centered around 1550, that's why I zoomed on it. Although the spectral characteristics has to be like parabolic shape. This is what is the LED input, and this is what is the light was going to be reflected from the grating and monitored at either east end or west end, depends on the setting of the phase shift. Now, in this slide here, I'm showing you, for example, if the temperature changes from 0 degree to 100 degrees, how the peak can be shifted. And on the other end, this is the transmitted signal. You have the depths of the signal at these locations. If you use a spectrum analyzer, you should be able to detect these depths. But if you have only power meter, it's very difficult to measure them. So the option is to change the phase of the phase shifter, and then eventually you're going to see these peaks and you can measure them using a power meter, basically. Okay. So this is the description of the component which is used for synthesis of the FBG. Again, this is a grating on a fiber core, and it's the design of this grating is done and published. The measurement is published in this this reference. However, we used some of the parameters from the publication, and we created the grating which matches basically the measurements in here. And this is, again, this is some presentation and a separate webinar. You can look at it, but this is one major application of using gratings as synthesis for synthesis application. So you use measurements basically to design the grating and make sure that eventually you can use the model which you create of the grating to do other characterization. Okay, so the final thing here before I go to the examples and live examples is to describe the vibration sensor based on relay backscattering, and this is known as a Phi OTDR. The design is you have a broadband source here, light source, and then you emit it through the fiber through a circulator. Now this is you modulate this laser, for example, with some narrow pulses. The narrow pulses determine the resolution of your measurement. So these pulses, if it is, for example, 10 nanoseconds, you're about 1 meter resolution. And then eventually the light, when it goes through, or the pulses which goes through the fiber, it's going to be reflected at different locations. And this back reflected relay scattered signal is going to be collected using a photo detector. The form of this back reflected signal is given by this formula, which depends on the attenuation and the length of the fiber. The model here we used in the to design the component, which is the Phi OTDR. It based on dividing this length of fiber into sections, and each section we divided it into n section, for example, and each section is a length of Li over n, and then each section has a reflection coefficient. It's called scatter coefficient, and it has acquired certain phase. Now the intensity of the total intensity collected by the photo detector here would have this kind of form, assuming that all the scattering coefficients are constant. As you see here, R is constant in this formula. Now, once you use this formula, you do some kind of FFT, and we can get this kind of measurements where it would tell us, for example, what is the location of the vibration. So if we have vibration at 10 meters, at 20 meters, and 30 meters, this vibration frequency, we can get them. For example, in this scenario, we have 100 hertz, 300 hertz, and 100 hertz again, the different frequencies. This is some kind of settings which you can control the laser line width. So you can control the number of vibration in the model. You can have one vibration or multi vibrations. You can control the line width of the laser. You can control the frequency. You can control the length of the fiber, the number of scattering. So you have lots of flexibility in this model. Again, we're going to make a separate webinar on the Phi OTDR very soon. Okay, so before we go to the question and answers section, I'm going to go into the examples where I'm going to show you the two examples. The first example here about the using the loop mirror as a switch, where in the OptiSystem you find this example. In this example here, you have a coupling ratio doesn't equal to 50%, which means the light on each clockwise and counterclockwise will have different value. And then this goes through the nonlinear fiber here. And eventually what's happened is each component will have different phase once it's propagated through the fiber, and a phase difference occur here, and the switching mechanism will happen. So this takes about less than 1 minute to run. It's before going there, you might see, for example, this is linear fiber, which is based on a bidirectional component. You can set in this component different parameters as depends on the commercial fiber you're gonna buy. You can enter the values for all the parameters and include whatever effects you wanted to do, and then eventually you can run the simulation. If you run it, again, it's gonna take about 1 minute to finish. During that, I'm gonna look into some question. So one question says why we are using, for example, LED instead of CW laser. First of all, is the laser dates will be more expensive to use, and the LED will much cheaper. This is the main advantage of using LED. Plus, if the LED centered at certain frequency and the grating has to be matching within that frequency to detect it. If it is off, then you will have troubles detecting the laser basically, and you lose it. We have here in this example 50 sweeps, so we sweep over the power level of the laser between 0 watt and 2 watts, and you can monitor the here the sweeps numbers. Now it's very close. Another question here we have saying when OptiSystem 16 would be available. So the target right now is to have OptiSystem around November time frame, and hopefully we can have an update sometime later on. So another question here we have about is it possible like to have the sensor in a full optical link where we have, for example, amplifiers and dispersion compensation or all these things. Again, the advantage of OptiSystem here is with the sensor application and modeling, you can have you can build your own whole system from all components. Let's say you can add up EDFAs, Raman amplification, whatever features you wanted in the system. You can control the transmission fiber characteristics and all these things, so to allow the transmission. Okay, so now the calculation is done. If you look here, we created for this example a report, and this report can show you, for example, the transmitted power as for every iteration where the power level is changing from 0 watt. So when you have 0 watt, you have no power transmitted, but you have, for example, at certain power level, you can have certain amount of phase where you have the light is going to be basically switched to the transmitted path instead of going back again to the reflection path. So this is the first example, which is, again, you can find it in OptiSystem. The other example we're going to run is the fiber loop mirror example sensor, which is we talked about it today. So this example, this is the DC bias which control the laser diode. So the laser diode here, or LED, you can have the center wavelength, and then you control the bandwidth, and then you control the, for example, if you wanted noise to be generated, seed noise and whatever. Once you set it up, you have a circulator. Circulator is bidirectional circulator, and then using a directional coupler. So the directional coupler here, the coupling ratio is 50%. You can also include noise in this coupler, for example, or no noise in it added, so you control it. Passing through the grating, now this is the important component which we need to put some more time on it. So the component here, as you see, the grating has the specification where you have the original or the Bragg grating wavelength, which is your wavelength defined at the reference temperature. And then you have other parameters here, like, for example, the effective index modulation, length, and you can control the reflectivity or bandwidth using some parameters if you click, or, for example, setting, if you want to define physical parameters or not. Then you have in this tab the sensing parameters. So the sensing parameters you have, for example, if you want to include temperature or stress effect or strain effect, so you can click on the effect which you need to include in the simulation. Okay. Now, if you, for example, you want to load files, you can load your own files. So you click here to load the files from the destination files. For example, this is temperature file. You can load it from library or you create your own. You have to make sure that the format matches the information which is designed. So if you can go to the help here, and in the help, basically you can look into the parameters of the grating, and every parameter is described and the theory about it. All of this information, you can find it there, basically. Then once you define the sensing capabilities, you can enter parameters, for example, for Young modulus, Poisson ratio, photoelastic coefficients. Then basically you define if you want to the noise levels for the grating, and then once we do that, your setting for the grating is done. And again, you can set the phase now shifter here. Phase shifter is 0. You allow the output to go into, for example, going back again to the transmitted path, the reflected path, or going to the transmitted path. If you set angle to 180 degrees, you may, if you like, do some kind of sweeping here to go or different angles, and you can see the effect of the angles, or you can see effect, for example, for the coupling ratio. You can sweep here as well. And then once you sweep, you can go over different coupling ratios and see the effect, how is the signal levels. In this example, if I run it here, also it takes about 1 minute to do. And once you set it up, here I did the temperature going from, I'm gonna show it to you once it's done, between 0 degree to 100 degrees variation. Okay, so I have more questions here. So the question is it possible for the data acquired from the sensor system to be logged in a database and analyzed for patterns that could provide useful information? Okay, so all the information in the OptiSystem, you can download this data in text file or Excel files. All this is accessible to the user, and you can do post processing on it. It's exactly similar to OptiSystem, all OptiSystem applications. Another example here, it says comment on the possibility of using machine learning in processing fiber optic sensor data. So the sensor and the synthesis capabilities, basically, because you can provide measured data, and the measured data you can use it to synthesize the grating design. So basically, you can try to use data to find the proper grating parameters, and then use these parameters into your modeling later on. Another question is it possible to make our own sensor? Yes, that's exactly what I was saying. Is the grating at this moment is the design parameters of it doesn't give you lots of flexibility. However, the component which is coming in OptiSystem 16 will give you a full freedom to design your own grating and use it as a sensor. So to provide you the sensing capability as well as capability for designing the grating as what you do basically in almost what you do in Opti grating. Okay. So the simulation is done here, as you see, and then basically what you can do, you can look at the this is the signals. Okay. So now, if you look at the effect of the temperature, the grating here, what I did in this sensing, I swept the temperature from 0 degree to 100 degrees, and as you can see, the responses every sweep. This is at 100 degrees, and you can go how it basically moves the center wavelength with the temperature as defined in the equation which we provided before. Another example, which is in OptiSystem. This example, which is it's a standard representation of OptiSystem, and this is documented already in all releases of OptiSystem 15.0 and 15.1. You have the grating in the standard format, and this is where we said we have the grating closer to the location. And if you run this example, you can see the grating, for example, here. It's set to have strain in it effect, and this strain is coming from a data file which is this data file here. If you open it, you can, the data file give you, as you can see, I'm gonna see here. Okay, so this is the parameter you can enter for the strain. It's gonna go from 0 10 minus 0 strain up to 60 10 minus 5, 70 10 minus 5, and then goes down to minus 50 10 minus 5. So all of these values, once you enter it in the file, and then you can run the simulation over it. And that's why if you remember in the presentation where we showed you the center wavelength drifted, and also the temperature here changes. You can read it from another file, which is temperature.data file. You can set up your temperature. As you can see, for example, here the format, you can put it as integers or fraction, as a single vector. Again, you can, once you set up the sensing parameters, all the center wavelength and everything else, here you can see this wavelength is at 15, this grating at 1560 nanometers, this grating at 1555 nanometers, this grating is set at 1550 nanometers, and this grating is set at 1545 nanometers. So once you do the measurements later on, as we showed you in the example, just to save time, I'm gonna basically if you can see here, basically the example. Okay, so you can see the center wavelength basically tells you what is the location. The amount of shifts here tell you the effects, and then again you can synthesize and separate the temperature from the strain and so on. With this, I guess I'm gonna conclude the presentation. I'm gonna look into if there's any more questions. Okay, let me see here's question. Okay, so the question says again, just to elaborate on the LED and CW laser. If you look at the, let's say here, if you go on the design of the grating, let's take this example. Now, if I put LED here, the LED basic LED or broadband source, the broadband source, if there is a drift in the center wavelength, especially with narrow band grating, then you should be able to reflect, if you have a light emitting diode broadband, so you reflect the band which is Bragg grating wavelength, and the other wavelength is going to pass through. Now, if you have a laser diode in here, and this laser diode is set at 1550, and the grating is set at 1560 nanometers, then basically the grating is going to be transmitted. All the light is going to transmit it, and there is no light is going to be reflected here, and you will not be able to measure anything. So that's the advantage of using LED for in this kind of application. Unless you have, for example, a mechanism to track the laser, which is very, very difficult. It's recommended to use an ASE source and or LED for this application. Okay, so another question here says, please comment on possibility of using using machine learning for data sensor. The data of the grating, which again here the example which been done with the salinity example. So the data, if you enter data into your model, you should be able to design the grating parameters, all the grating parameters, and then you can synthesize the grating with measured data. Okay. Some questions about acquiring the video. The webinar would be sent to all registered registered of the webinars by about after 1 hour. And I think it's with this I'm going to conclude the webinar. I thank you very much for attending.